We talked about the layers of the atmosphere. The layers of the atmosphere. So now we're going to talk about the atmosphere moving. And we all know the atmosphere moves because we feel the wind, right? Feel the wind. We get up in the morning, we watch the weather on the news. Those storms move all over the place. So there's a storm hitting Northern California right now. It's going to head our way, but it's going to dry up before it gets here. So we know things move around. So something has to make them move. And what makes them move is something we already talked about. Uneven heating of the earth. Some parts of the earth are heated more, some less. All because the earth is round. And we studied this way back at the beginning. We talked about the energy balance for the earth. And we said a lot of it had to do with the angle that the sun was hitting. So if the sun comes straight down, it's going to hit an area that big. So all the energy will be there. But if that same amount of light comes from an angle, it's going to heat the same area plus some more. Because you put it at an angle, it spreads out. Does that make sense? So I'm heating a bigger area with the same amount of energy. So it's not going to get as hot when it's spread out as when it's straight up and down. Seem reasonable? If you spread the light out, it's not going to heat as evenly. It's not going to heat as much. Okay? So you concentrate the light by making it straight. It heats up a lot. From an angle, it heats up less. It doesn't matter which side you come from, right? So that comes into play because the Earth is a sphere. The Earth's round. So that the energy is going to vary from latitude. Latitude is how far north or south you are, to latitude. So we talk about high latitudes. 0 is straight up on the equator, and all the higher numbers mean close to the North Pole. It'd be a lot easier if you just put that phone in your pocket. Okay. So there's the Earth. Where it hits the equator, it's hitting it straight on. That much area. But if it hits up there, it's got to hit much bigger area. Same amount of light, much bigger area to heat. Oops. So that what this is trying to explain is why it's warm at the equator and cold at the poles. And it works at the North Pole. Oops. And the same thing would happen down at the South Pole. So both poles are cold because they've got big areas and because they're hitting it at a big angle instead of straight on. Make sense? So we got the equator's heated, the pole not so much. Okay? Now, we said straight on the equator. It's not always straight on the equator because the Earth tilts. So that at the beginning of spring is when the sun is directly over the equator. So it would be direct sunlight here on the equator. And where we're at, we've got this much area. Okay? That's Southern California. But as I move into summer, notice how the area has gotten smaller because I move closer to straight overhead. So it's warmer, it starts warming up in the summer. Then at the beginning of fall, it's straight overhead again, and we're right back to where we were at the beginning of spring. And then in the winter, we've got a bigger area. So it's got a bigger area, so it doesn't warm up as well, and it gets cold here. So the place where it's directly overhead moves up and down a little bit, and the actual lines that it moves are called the Tropic of Capricorn, the Tropic of Cancer. That's as far north. When the sun is directly overhead here, it's the beginning of summer. When the sun's directly over here, it's the beginning of winter for us. Yeah. You studied the seasons before, just reminding you of those. It's about the tilt of the Earth. Okay. So we got some uneven heating, and the equator's heated more. The equator gets more heat. So think about yesterday, what happened to the fluids when you heated them unevenly. One side got heated and the other didn't. Well, where it got heated, it rose. So near the equator, the air is rising. And it rises because it gets lower density. Well, if the air is less dense above you, then the air above your head weighs less. Does that make sense? If it expands, it spreads out, there's not as much air over your head. So as it expands, gets less dense, you have less air over your head, less pushing down, so there's less air pressure. We call that low pressure. Now, where it's cooler, it's more dense. So where it's cooler, if it's more dense, that means the air has been pushed together over your head, and you have more air molecules over your head. So there's going to be more air pressure. And this means that in the places where it's warmer, it's going to be rising and low pressure, and where it's cooler, it's going to be colder and low pressure. So near the equator, it's going to be rising. Further on, it's going to be sinking. And that pressure difference is going to make the air flow from the high pressure to the low pressure. And that flow from high pressure to low pressure we call wind. Now, you happen to live in a place where you get to see the examples of this every winter. See, what do you mean you get to see examples of this every winter? Well, every winter here we get the Santa Ana winds. And the Santa Ana winds happen when there's a high pressure over Nevada. High pressure over Nevada and low pressure off the coast. So the air wants to move from the high pressure to the low pressure. But there's a mountain range in the way. Okay? So that while the wind is moving gradually, when it hits that mountain range, it gets funneled in through the passes. And we get the Santa Anas. That's us, by the way. This is Orange County. So we get Santa Anas because high pressure sets up over the desert, low pressure offshore, flows from high pressure to low pressure, and it gets squeezed as it goes through the canyons. And it gets squeezed, it goes faster. And when it gets squeezed, it gets hotter. And that squeezing, making it hotter, is what you'll notice you got a Santa Ana when it's warmer in LA than it is here. That warm wind is blowing down. The same winds happen in Northern California. They call them the Diablo winds. They happen in Montana. They call them the Chinooks. The same kind of thing. You get high pressure to low pressure. It squeezes as it goes through a mountain. You get some strong winds. Okay. So that energy is going to move by convection currents. That's why we looked at the convection currents yesterday. So how do you make the convection currents? Well, we said near the equator, over here, it's a different color. So over here, I changed colors, why didn't you? Right near the equator, that's where you're getting the direct sun, that's where it's hot. And that hot air rises. So the warm air near the equator rises. But it doesn't leave a vacuum behind. Air has to come in and fill it. So there's got to be some air coming to fill in for the warm air that rose. Now, where it came from was someplace where it's cold, so that cold air is sinking. Warm air rises, cold air sinks. But there's got to be something to replace that, and that's the air that used to be warm, as it stays up there, is going to be cooler because it's away from the earth. It's not getting heated anymore. It cools off. So I get a circular motion of air. And it's going to happen both in the northern hemisphere and in the southern hemisphere. The sinking air here, rising air there will make a convection current going that way. So we get convection currents. Now, what happens to that warm air? The way it gets cold is it gives off its energy to space. So warm air rises, gets replaced by cold air. We end up with convection cells. That's why I had you look at those yesterday, because they're big drivers of what we see on Earth. Okay. So warm air rises near the equator, replaced by cold air from close to the poles. That warm air emits the energy into space and cools down. So you'll notice that near the equator, the winds blow towards the equator no matter which side of it you're on. Right? And since it turns out that the equator is 0, and there's 30, 60, and the pole is 90, so about a third of the way up, from about a third of the way up, it blows towards the equator. So that loop of air that rises, then falls, and comes back down, that's what we call a convection cell. So it's easy to see why a convection cell forms at the equator. You got hot air, it's got to rise. Something has to take its place, so cold air comes in behind it, and you get circles. Another place it's easy to see why a convection cell sets up is at the poles. Because at the poles, the opposite happens. At the poles, it's cold here. Cold air sinks. When it gets near the surface, it gets warmed up and it rises. So that cold air that sinks gets replaced by warmer air from the south. And as it sinks, it's going to have to move south to get out of the way. So the winds blow towards the equator at the poles too. The winds want to go towards the poles. So I've got one convection cell at the equator, I've got one at the North Pole, and in between them, between 30 and 60, the other two convection cells make a third convection cell. We already knew that the air was sinking here for the equator, to go to the equator, and it was rising here to go to the poles. But it can sink here and go north. Sink here and go north. If it does what it's supposed to do. And the rising air can go south, so that you end up with 3 convection cells as you go north and 3 convection cells as you go south. The one in the middle is caused by the one on each end. It's got to sink at 30, it's got to rise at 60, so you can make a convection cell that does that as well. So when it's rising, it has its choice of going that way or that way, so it's going to make a convection cell either way. When it's sinking, it has its choice of going that way or that way, so it's going to make the 2 convection cells that way. So I end up with 3 going north, 3 going south. The ones near the equator, the winds blow towards the equator. The ones at the poles go towards the equator, and in between, it goes the opposite direction. But we never see those straight north and south winds. We don't see the straight north and south winds because the Earth spins. And when it spins, you think about it. If you're spinning a globe, how fast are the poles moving? Are they going anywhere at all? No, the poles aren't moving at all. But the equator is going, you got to go 25,000 miles a day. So it takes you got to go 25,000 miles in one day at the equator. But as you go north, going around once is not 25,000 miles anymore. Where we're at, it's probably about 17,000 miles. So we only travel 17,000 miles in a day. The equator travels 25,000. The equator is going faster than we are. And that difference in speed is going to affect the winds. So it's spinning at different speeds at different latitudes. We are spinning slower than the equator, but we're spinning faster than the pole. You take a couple steps south of the North Pole, you're going to go once around that pole in a day, but you're only going to go 20 feet. Whereas to go once around at the equator, you got to go 25,000 miles. Yep. So to give you an example of this and what effect that has, got a couple of short videos. The first one is just about this, why it bends. Let's see if this is going to work for us. 3, 2, 1. So this is at MIT, a couple of people on a rotating platform. They're just going to throw the ball to each other. You throw it straight back and forth, right? No problem. Because they're not spinning. But you start with spinning, if you try to throw, you'll miss every time. And notice they both miss to the right. Okay, so here they have, you're spinning, watch the path of the ball. You'll see the ball moves in a straight line. The ball's moving in a straight line, right? He's just throwing it to where he used to be, not where he's at now. But if you mount it to the platform, when you throw the ball, it looks like it curves. Is the ball curving? It looks like it, but we just saw that they were really throwing it straight. And that's the Coriolis effect. So now he's mounted it straight, so it's looking at him. So, and you'll notice it always curves the same direction, always curves to the right. And that's because of the direction they're spinning. So the direction you spin determines which direction it moves. If it moves you rotate the other direction, it goes the other way. Curving to the left for him. He's looking, it goes left. Does that make sense? So all you have to do is spin, and it looks like it's curving. And that's what's going to happen to the wind. It's going to curve because the Earth is spinning. Because when we look down from space, we're going to see the curve, not the straight line. So, this.
The last video showed that our atmospheric circulation is split into 3 cells in each hemisphere: the Hadley cell, Ferrel cell, and polar cell.
Okay, so they just gave the names for those cells. I don't care if you know them. They gave them names. That the ones closest to the equator are called the Hadley cells, and the ones on the poles are called the polar cells. And
in this third video in the global circulation series, we will look at the winds within these cells and how the rotation of the Earth influences these winds to give us jet streams and prevailing wind patterns. As well as being split into 3 cells, the global circulation pattern is at an angle due to the Earth's rotation. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so it has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and is moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere, and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere. How does this lead to eastwards flowing jet streams and prevailing winds? As air moves away from the equator at the top of the Hadley cells toward higher latitudes, it starts to be deflected by the Coriolis force. Just as a skater spins faster by bringing their arms and legs closer to their bodies, air moving away from the equator speeds up as it gets closer to the Earth's spin axis. This process is known as the conservation of angular momentum. the magnitude of the Coriolis force increases towards the poles. So by the time the air reaches 30 to 40 degrees north or south, it is moving in an eastward direction. This subtropical jet stream occurs high in the atmosphere between 12 to 15 kilometers. It is associated with some of the strongest winds on Earth, reaching over 280 miles per hour at times. As this jet sits between the descending branches of the Hadley and Ferrel cells, there is little associated weather. The polar front jet forms in a different way. This jet sits between the rising branches of the polar and Ferrel cells. It marks the boundary between cold polar air and warm tropical air, known as the polar front. The polar front jet occurs at a height of 11 to 13 kilometers and is primarily the result of the temperature contrast across the polar front. The stronger the temperature contrast across the front, the stronger the jet. So it follows that the polar front jet is stronger in the winter than the summer. Waves or ripples along the jet stream can cause Atlantic depressions to deepen explosively as they are steered towards the UK. Winds at the surface are also subject to deflection from the Coriolis force. The surface flow of the Hadley cells form the persistent trade winds. As air flows towards the equator, it is deflected towards the west in both hemispheres, forming the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The persistence of these winds allowed sailing ships to cross the Atlantic and opened up trade routes between Europe and America, giving them their name. The surface wind in the Ferrel cells would flow from a southerly direction in the northern hemisphere, but the Coriolis effect causes this wind to be deflected to the right, leading to the prevailing westerly and southwesterly winds often experienced over the UK. This setup is not unique to our planet. Jupiter also has circulation cells similar to those on Earth. A day on Jupiter lasts for about 9.5 hours, so it is rotating much more quickly than the Earth. The great size and fast rotation of this planet makes the Coriolis effect very strong. This splits the Jovian atmosphere into many circulation cells in each hemisphere, producing numerous alternating bands of rising and falling air and giving Jupiter a distinctly striped appearance.
Okay, so that's the Coriolis effect and how it affects the winds. Okay, so the Coriolis effect is that curved motion caused by spinning. Now, when I was in school, they told me that's why turn that off to put it away. They told me that's why the water in my toilet went the way it did. But that's not true. It goes that way because they put a jet in to make it go that way. But it causes the wind to turn to the right in the northern hemisphere. And left in the southern hemisphere. What I meant. Turns left in the southern hemisphere. So we get winds, and call them prevailing winds. That means overall, in general, that's the way it goes. Locally, a storm can make it go the other direction. But on average, it moves that direction. Now, when I was in school, they gave these names based on trade. Okay? Based on colonial expansion across the Atlantic. That's what the names. They use the word like trade winds, horse latitudes, the doldrums. Now the current names is all they do is they name the direction they come from. So if I say a northerly wind, that means it's coming from the north, not that it's going to the north. So we name winds on where they're coming from. So wind coming from the south is a southerly wind. One from the northwest is a northwesterly wind. Just whatever direction they come from. So like we saw in the video, as the wind flows towards the equator, it turns to the right. And in the northern hemisphere, that means it's going to come from this direction, which is northeast. Make sense? So to figure out where the wind is, which direction it's going to do, is in the southern hemisphere, it turns to the left. So they call the winds towards the equator from the north the northeasterlies, and the ones from the south the southeasterlies, because they're coming from the south, but they turn east because the earth spins. Okay. Now, notice where we are. We're right here. Right? So we don't see the prevailing northeasterlies. For us, the wind tends to come from it goes towards the equator. Sorry. The wind goes towards the equator. We're starting that to away from the equator. And the wind moves away from the equator. When it bends to the right, it's going to come from the southwest. So they call them the southwesterlies. As it moves away from the equator in the south, it moves to the left. So they call it the northwesterlies. So this right here, this southwesterly wind, is why when we're looking for weather, we look to see what's out over the ocean. Because what's out over the ocean is going to come towards us. Okay? We always look to see, if we want to see what the weather's going to be like tomorrow, we don't look at the Midwest, we look out to the ocean. Because that's where it's coming from because of those prevailing winds. And up north, they're coming from there, so they move from the northeast and from the southeast. And so when I was in school, they talked about these as the trade winds, because what happened is when they wanted to leave England to come to the U.S., they didn't sail from England to the U.S. Not in a direct route, because then they'd be sailing against the wind, and their ships were powered by wind, so that was kind of ineffective. Instead, they would sail south until they got into the prevailing northeasterlies, which would blow them across, and then they could come into the U.S. And when they wanted to go back to Europe, they'd sail north to westerlies, so they could go that way. Does that make sense? Hey. 11? No, we got 13, right? So, your homework over the weekend is to do the lesson checkup at the end of the atmosphere section. There's two ways you can do it. One is to open up the ebook, write your answers down, and send me a picture. The other, actually, open up the PDF of the book, write down the answers, send me a picture. The other is, if you go on the book, the electronic book, It's at the end of the thing and you should be able to answer it right there. If you do it online and without the picture, where it says you got to turn something in, just write down that you turned it in online. That make sense? I'll take it either way. If you've got the book in front of you, it's there at the last page of lesson 1 in unit 9. And if you got it online, lesson 1, unit 9, lesson check. Should be in the classroom there, but I'm not sure everybody got added yet. Have a great weekend. Remember the seating chart if you have any requests.